So our next speaker is Leo Sampaio Ferraz Ribeiro, who will present their work, Scene Designer, a unified model for for scene search and synthesis from Sketch. Leo is working on cross-modal modeling between images and sketches, which is applied to recognition, search, and synthesis of both domains since 2015. And she is currently a PhD student at the University of São Paulo. So now time is yours, Leo. Please start your presentation. Thank you. Can you share your screen now?
Yes. Okay. Can you see my screen or
yeah,
the window I shared? Okay. Okay. So I'm Leo, and I'll be presenting Scene Designer.
Please, can you make it full screen?
Is that not full screen?
Not yet.
Okay. My computer is hanging a bit. Oh, okay. I see. Yeah, it was sharing. Is that right now?
Yeah, all good. Yeah.
Okay. Okay. So I'll be presenting Scene Designer, and this work was done by me, to John and Moacir. And well, I should have said before, me and Moacir are from the University of São Paulo. Tu and John are from CVSSP at the University of Surrey, and John is also from Adobe. Yeah. Okay. So I'll explain what's the application scenario, how it works, and then we'll do a bit of a discussion on dataset results and limitations. So the application scenario is the following. We want to have a single model that is able to use scene sketches to do search and synthesis of scene images. And the idea is to combine search and synthesis to create this interactive workflow. So a user might do a search and then use the result of this search to take like the background of an image, combine this with the sketch to generate the individual objects. Yeah, so these are two examples of like leaving the objects and changing the background. And they also might mix sketches and crops of objects from the images to create new images as well. And our model is also sensitive to pose. As you can see this example. Well, didn't see a lot, but yeah. Okay, I have the volleyball wheel of death when the computer hangs. Let's see if I can do. I'm sorry, I know we are out of time. So, okay, it's just going over the animation again. We'll get there. Okay, so how it works, it's a pretty big model. It doesn't even fit in the whole slide with the title. So I'll go over each step, right? So the first thing that we do, that's in the A bit over there, is that we pre-train a traditional triplet search model. So it's loading, but it will load. So what we have here as input is individual sketches, so like crops of the scene, and individual object crops. And those are trained with, okay, now it loaded. So yeah, individual object sketches and object image crops. And those are trained with a pre-trained mobile net. So make it really a small model to do triplet training as people usually do for SBIR, right? So at this point, there's no information on on how these sketches connect. They're just individual objects, yeah. So this is our mobile net, and I'm sorry for my computer just kind of hanging. And the output is also trained for classification because that helps with the optimization space of the triplet, because it has a problem of staying on the margin. Yeah. So this is the first step. On the second step, we connect everything and train everything together. And this triplet also keeps training so that we don't lose the information that we learned here. So what we have now at this point, we have for each object, we have an object level representation, right? But we also know that these objects are in a scene, we know where they are, and we can infer a scene graph from this. So the scene graph is a graph of the objects, and the connections are, they describe the relationships. So like above, below, to the left, to the right, inside, and surrounding. So we apply this graph to those object level representations, and we get them through a graph neural network. This graph neural network will also have as input a relationship embedding. So each type of relationship will also learn some kind of a vector as well. And this will give for each object what we call a constrained correlated relationship, representation, sorry. And we call it that way because it is constrained by the graph, by the relationships that each object has with one another, but it is correlated much more than the object level one because, well, it's been through a graph neural network, so there is some correlation between each object. And the next step, we go through a transformer. So we add a positional encoding that's based on a grid. So it's a 5x5 grid, and we make a positional encoding that uses that grid to place the objects where they are. And the transformer is important because now we don't have any constraints about what the relationship between the objects are. So the model can learn whatever it needs to learn between all the objects to all the objects without a constraint of a specific relationship between them. And what we also do with the transformer is like you would do with a bird, we have a class vector that starts at 0, and this vector learns to be our scene representation. Yeah. And the scene representation, that's a single vector. We train this vector with our novel, our novel contrastive loss. And we use this for search, basically SBIR, but for scenes. And all of the object vectors that we get as output from the transformer, we train them to generate masks and bounding boxes so that we can build a semantic layout. And we use the semantic layout as input to an layout to image generator. In our case, we did use the Gauguin or Spade from NVIDIA, and we get an image as output. Yeah. So some extra tidbits. To train a model that is this complex, it's not very large, but it's very complex. We started trying to use Sketchy Cocoa by itself, but it's a bit small. So we wanted something bigger. So we reframed 2 data sets to make a new one. So we call this Quick Draw Cocoa. So what we do here is a soft pairing between images in Cocoa and the objects in Quick Draw. So we did like a huge map from one kind of class to the other, and we were able to match 92 classes from the total 180 from Cocoa. And in this way, we have multiple scene sketches per scene, and Quick Draw is gigantic. And by combining those, we have almost infinite scene sketches to train our model on. And then we fine-tune this model on Sketchy Cocoa, and it gets better at posing and stuff. So our results, these are our search results. These are some examples. We were able to do better than Scene Sketcher. That's the previous work that did search SBIR with scenes. And we try to compare with other models that do SBIR, but single objects. But naturally, since they have less information, because they don't know the individual objects, they do not perform close to Scene Sketcher or our version as well. And you can see here that even in failure cases, the context is pretty good. See, you have kitchen scenes or inside scenes here. And we have like this little truck, and it did find cars and roads, and it should find a plane, but that's okay. It's like the scene of transit. And this, well, this is more results. Oh yeah, the previous results were Quick Draw Cocoa, that's 92 classes, and those are Sketchy Cocoa that has 14 classes. See, there's mostly animals and planes are in Sketchy Cocoa as well, and cars. Okay, for generation, these are some of our example results. So the first column, we have examples where we do only sketches. Then on the second column, we mix sketches with images, because since at the start you had this common representation between the images and the individual sketches and individual object images, we can mix and match the two modalities when building the composition, and everything else after that first part of the network doesn't care if it's a sketch or an image, it would just work. And we also show some pose control here. Pose control, we hypothesize that it's learned because it's a common representation and it's able to learn from the image, and that transfers for the sketch, even though the Quick Draw Cocoa dataset does not match the poses of the sketches with the image crops. And well, the biggest limitation that we have is that we don't take backgrounds into consideration during the modeling, the entire modeling here. What we do is expect the user to choose one of the images and take the background from that. And by taking the background from that, I mean taking the semantic map of the background, or coarsely drawing that background would also work in the same way like the Gauguin model, the spade model. The other problem that we can see, and we can particularly see, I guess, here, is that there's no way for us, or at least the model is not very good at predicting depth, right? So I guess we could collaborate with Sketchy Depth, the previous talk, to talk about fixing that. So we use a heuristic in which bigger objects go in the back and smaller objects go in the front, but still not all depth perception results are perfect. Sometimes we place the objects in the semantic layouts in the wrong place because they do overlap, and then you have to choose which one will be in front of the other or not. And well, that's it. See our paper, and we have the code available on GitHub as well for you to try. And now questions. I think I was too quick.
Yeah, thank you for this interesting work. And any questions? Yeah, the first one comes from Song. Please.
Thank you, Leo. Are you still in the UK, or have you gone back?
No, I have gone back. I have gone back for, it's been a year already that I have gone back to Brazil.
Right. Anyway, time flies. Yeah, I mean, great work.
Yeah.
So one question, basically, it's not a question, it's for a comment, really. So what do you think, apart from the size of the data sets of scene sketch is too small, So what do you think are the other problems with the scene sketch datasets nowadays? So if you were to, if you have the money and the resources and the time to build another scene sketch dataset, so what would be the, the ideal one in your mind?
Oh, that's very interesting. I think one thing that we don't have a lot, I've seen one small data set that does this, is that both Sketchy Cocoa and our Quick Draw Cocoa are not meant to be scenes. So those objects were drawn by themselves. So the drawer didn't think of the relationship between the objects. So when we synthesize a sketch, a scene that's like someone is holding an umbrella, of course, the synthetic version of this is that the umbrella is kind of hovering over this person because no one drew that intentionally. So I guess having intentional scenes would make this work more reliable, because people, when they draw scenes, they don't draw one object and then another, then another.
Sure. Is that holistic understanding, holistic abstraction that's missing, right? Yeah.
Yes.
Okay.
Yeah.
Thank you very much. Yeah.
Thank you. Yeah, I also have a question about the dataset. So you use the quick draw dataset to synthesize the objects in the real images. But I noticed that is there any difficulty to choose the object that there is no object in the quick draw? I mean, there is no good candidate to synthesize the objects in a real image, right?
Yeah. So there was a lot of manual work because so Coco has some weird classes like furniture, and we try to mix all the furniture in Quick Draw and train the model like that, like randomly selecting furniture. But of course that doesn't work because a bath is a furniture, but that's not a furniture that you synthesize in a living room, right? So we had to cut the furniture out completely. And another good example of this is that Quick Draw, and I don't know if anyone knows of a data set that has this, but Quick Draw doesn't have stick man figures, which is a weird choice, right? You would think that drawing humans would be something on Quick Draw. So we took a very weird choice there, where we place yoga sketches in place of humans on the Coco dataset, because most of the yoga drawings are stick figures, even though their pose is not great because they are usually like posing for yoga. They are stick figures, and that's the closest we could get to humans.
Okay, yeah, thank you. And yeah, another question about the framework. Did you try to use the outputs from the graph network to apply to the retrieval problem? As I can imagine, the graph network can also model the relationship between objects, and the messages or the information can propagate into each other to represent the same. So did you try to use that for retrieval?
So yes, we did ablation studies where we used only the graph neural network and only the transformer, and neither of those work. And this is not in the paper because it's kind of work from the future, but we are studying now exactly why this happens. And one thing that made the GNN much better was adding the positional encoding that we had on the transformer on the GNN, and that makes the GNN by itself, without the transformer, get a much closer result to what we get with both of them. And we also are trying to do the same thing with the transformer, adding the relationship information through relational positional encoding for transformers. to the transformer, and then we get also a closer result to Scene Designer with only a transformer. But neither of those get as good as using the GNN followed by a transformer. So we're still investigating what is the exact architecture thing that happens that combining those two makes it work so much better.
Okay, great. Thank you so much. So yeah, very interesting work indeed. I think this is a very good work because this work poses very important problems in Sketch community, which lift the Sketch problem into a scene level. And also the dataset is also very crucial for further improvement in our Sketch community. So yeah, maybe we can discuss this later in the panel discussion session. Okay. Yeah. Thank you so much. Yeah, maybe, yeah, it's time to move on to the next session.